Hi everyone, welcome back to my channel. Today we are going to talk about the sorting algorithm which is called as quick sort. So this is again another video in my sorting playlist. If you have not checked out what is sorting, why do we need sorting, then please check out my previous videos. There I have mentioned what sorting is, why do we need it, and also certain standard algorithms like bubble sort, insertion sort, and merge sort I have already covered in that playlist. Do check those out. Alright, coming to quicksort. Quicksort is a sorting algorithm, okay, which has a lot of practical applications. It is based on the paradigm of divide and conquer. If you do not know what divide and conquer is, please check out my merge sort video. In that, I have explained what divide and conquer is in detail. So merge sort is another example which uses divide and conquer paradigm. Quicksort also uses the same. Second thing is, we had spoken last time about something called as stability in a sorting algorithm. For example, insertion sort. Insertion sort is a stable algorithm. In that video of insertion sort, I have explained in detail with taking a practical scenario how does stability in a sorting algorithm is useful, correct? So do check that out if you have any doubts. So quicksort is an algorithm which is not stable. Quicksort is an algorithm which is not stable. It is based on divide and conquer paradigm, right? But it is extremely useful in sorting large data sets. If you have large data sets, then quicksort is your go-to solution. Like we had seen in the previous video of insertion sort was a very good option if your data sets is small, or if your data is partially sorted, or if you want a stable algorithm, right? But quicksort is the solution if you want your data, if your data is very large, then is when you use quicksort. Some of the practical applications of quicksort is, one, in Java, there is a arrays.sort, that is basically an inbuilt function given by Java language to sort your array. That particular arrays.sort, that function behind the scenes uses a version of quicksort to sort your array. Okay, other applications are actually, like for example, in compression algorithms, in database management systems, in operating systems, on all of these places, quicksort is being used. In fact, wherever stability is not required, quicksort algorithm is being used. Let's dive into the algorithm. Let's talk about quicksort algorithm. Let's start with the intuition of the algorithm, how this algorithm actually sorts your data, correct? So again, as usual, we are going to try to sort our numbers in ascending order, right? So the numbers which I have here is 4, 1, 3, 9, and 7. For quicksort, we basically need two kinds of concepts. One is this algorithm sorts your data based on the concept of divide and conquer. And the second thing is it uses partition algorithm. So let's talk about each one of them. Divide and conquer algorithm, this is basically a paradigm. That means there are certain kinds of algorithms which are being classified as divide and conquer. This divide and conquer means they solve the problem by dividing the problem statement into smaller sub-problems. You find the solution of those sub-problems and then combine the solutions to find actually the solution of a bigger problem which you actually started off to solve. The meaning that suppose if my data is of size n, I might divide this data into smaller sub-problems. Just giving an example, might be I divide this n into two small sub-problems of n by 2 and n by 2. If I have to solve this problem by divide and conquer, I will at least have to divide my data at least into two sub-problems. Okay, so here I have two sub-problems. I'll solve this sub-problem and so I find the solution of it. Let's say the solution for the first half of n by 2 is S1 and the solution for the second half is S2. Now I'm going to combine this solution so as to find the solution S, which is actually the solution for the main problem which was of size n. This is actually in brief what divide and conquer does, right? If you still have doubts or if you still want to understand and visualize how divide and conquer works, you can check out my video on merge sort. I have one dedicated video where I have spoken about how divide and conquer algorithm actually works. So you can check that out, right? So here quicksort is again based on divide and conquer, meaning that here also we are going to divide our data. So your data, what we'll have, you basically have a bunch of numbers, right? We have here 4, 1, 3, 9, 7. We have these 5 numbers which you want to sort in ascending order. So we are going to divide this data, divide this array into smaller parts, sort those smaller parts, and then combine them into one main ascending order array, right? Now to do that, to do this, we are going to use something called as partition algorithm. Okay, now let's talk about this partition algorithm, right? So now let's say you had this 4, 1, 3, 9, 7. Let's divide it into two halves. So 4, 1, 3, 9, and 7. Okay, let's call this is first half. Okay, let me call this as part 1, and this is the second half. All right, now because it's divide and conquer, you divided the problem into two parts. Now you're going to solve the problem of sorting for the first part of the algorithm, correct? Now to sort this, what again you're going to divide this, right? Because it's divide and conquer, you keep on dividing this, right? And finally you find the solution and you combine it, correct? Now, where does partition algorithm really come into picture? Let's talk about this. Now here, see, because I have divided this in between, correct, right? This is what usually a divide and conquer will do, right? Because where you find the mid element and you divide it, right? That is also we do similar in the case of merge sort also. But here we are not going to divide simply by finding the middle. What we are going to do is we are going to use partition algorithm to perform the division of the data. That means the data which you have 4,3,4,1,3,9,7, correct? We need to divide this data into two or more subproblems. In the version of quicksort, in this quicksort version which we are going to study, we are going to divide this into two halves all the time, right? So when you divide this into two halves, I exactly need to know where should I begin my half. Should I consider this as part 1 and this remaining as part 2, or should I divide here, or should I divide here? The answer where should I divide actually has been given by the partition algorithm. Okay, so let's talk about this partition algorithm. Partition algorithm is nothing but it partitions your your array. So suppose you have this again 4, 1, 3, 9, 7 as your data, right? In this, there is a concept of selecting a pivot element. You can even pronounce this as pivot, whichever you prefer. So I'm going to call it as pivot. So there is the concept of choosing a pivot element when in a partition algorithm. And let's say I choose always my first element of that subarray, which is given for me to partition as my pivot element. All right. After you choose this 4 as your pivot element, you are going to perform partitioning on this array by using the partition algorithm. The output of the partition algorithm is going to be such that your pivot element, which is number 4, is going to be placed in the correct position where it should be if your entire array is sorted. Meaning, here I have what 4, 1, 3, 9, 7, right? So let me write here 4, 1, 3, 9, 7. This was my input, correct? This is my pivot element, right? If I had to sort this array in ascending order, where would 4 come? After 1, it is 3, then 4. 4 should actually would be placed at this position. This would be the correct position of 4. That means the position where the element would be placed after I finish completely sorting the array. Correct? So partition algorithm is going to place this pivot element in its correct position, the position where the element should be after you have sorted the entire array. All right. All the elements to the left of it, to the left of this pivot element, are going to be less than or equal to pivot. All the elements to the right of it are going to be greater than pivot. So your partition algorithm, so this is the output of partition algorithm. What is it? Partition algorithm is going to take the array or the subpart of the array which you send it. It is going to choose a pivot element. Let's assume I have chosen always the first element of my sub array which I am sending, okay, to the partition algorithm as a pivot element. The output of my partition algorithm is nothing but it is going to place this pivot element in its correct position, okay. All the elements and for the remaining elements, right, all these remaining elements are going to be rearranged in such a way. All the numbers which are less than or equal to 4 are going to be to one side. All the elements which are greater than 4 are going to be to the right hand side of 4. Okay, so here if I apply this to this algorithm, to this particular data, what I'm going to get is after I perform the division. So here we are using, in quicksort, we are using this partition algorithm to perform the step of what? Dividing your data, right? It's the first step in your divide and conquer algorithm. So here what I'm going to do is after I run through this partition, my 4 is here right? I'm going to add 3 and 1 here and remaining data 9 and 7 here, right? That means now you have divided your main problem, which had 5 elements, now into 2 small subproblems. One subproblem has 2 elements and another subproblem also has 2 elements. Now what you have to do is again apply quicksort algorithm, which is the part of division, to this. You have to now divide this, right? This is the essence of using divide and conquer. So now I'm going to apply partition algorithm for the part 3 and 1. So here also let me choose this number as my pivot element, right? If I choose this as the pivot element, what does my partition algorithm going to do? It is going to place 3 in its correct position. The correct position of 3 is here. All the elements less than or equal to the pivot element are going to be to the left of 3, which is nothing but there's only one element, right, which is 1 and 3. And are there any elements greater than the pivot? No, right now, because in the sub array which we have sent to partition has only 2 elements, right? So only one element was there which was less than or equal to pivot, which we have added here, right? And you're going to have 4 as it is, 9 and 7 as it is, right? In the next step, we are supposed to solve the subproblem which has 2 elements, 9 and 7. Again, for this, you would use the partition algorithm. Here, what you're going to do is this will be your pivot element. Pivot, when you have this after partitioning, this 9 is going to be in its correct position. So 9 would be here. All the elements less than or equal to the pivot will be to the left of it. In this sub array, what are the elements less than 9? 7. So that will be present here. Then you have 1, 3, 4, 7, 9. And this is how your entire array will be sorted in ascending order, right? So 2 things to remember when it is a quick sort. First thing, it is going to use divide and conquer, right? In merge sort, if you talk about merge sort, we had used a simple formula. You just find out the middle element in your array, correct? But when you're trying to divide it, here in quick sort, we are going to use partition algorithm to basically find out the division. Basically, we're going to use partition algorithm. Partition algorithm will place the pivot element in its correct position. By doing so, it is dividing the array into 2 parts. All the values which are less than or equal to pivot will be in one part of the array. All the elements which are greater than pivot will be in the second half of the array. And this is how it divides your array into 2 parts. Now you can again apply quicksort on this half. Again apply quicksort on this half. And this will continuously keep on doing this until your entire array is sorted. Hope this helps. Now let's go and look at the code. Now let's try to write code for this quicksort algorithm, right? Yes, we have still not looked at how the partition algorithm works. Let's first write a simple code for this divide and conquer part, right? Where you can basically continuously dividing the element. Let's assume that we have a partition function, right? So if you remember from the merge sort solution, right? If you have not checked that out, I would really recommend just go and check out merge sort video. It will really help you in understanding quicksort better, right? So here, if you see that what we have done is, I'm going to have 2 pointers, right? I'm going to say, like, suppose let's take this numbers which we had is 4, I think 1, 3, 9 and 7, right? Let me say this is the index, the lowest index, and let me say this is my highest index, right? What you're going to do, because you're applying your divide and conquer, right? We are basically going to need to divide the this array into 2 parts, right? Now, how do we decide where to divide? That where to divide is given to us by the partition algorithm, right? And this partition algorithm will divide the array into 2 parts, and we can continue doing this until where should we keep on dividing our array? We should keep on dividing our array into smaller subproblems unless and until there are at least one element present in the subarray. Meaning, suppose if I get a subarray, okay, this is my subarray which has only one element. Let's call that element as 8, right? If there's only one element, do you think you should divide it? No, because our entire point is we keep on dividing until we get a subproblem. Once we get that subproblem, we solve that subproblem. Okay? Now here, when you're low and high, both are going to point here to the same number, right? That means when you have a subproblem which is of size 1, that subproblem is already sorted. You have to stop your dividing step, and now you have to start conquering it, right? Basically finding solutions to the subproblems which you have created so far, right? So how do I do that? I can achieve this by writing a simple condition. If low is less than high, then only do the part of dividing your array into smaller subproblems. Why? Look at this. when you have numbers like this, right, here total we have 5 elements, low index is going to be less than high. Why? Here the index is 0, this is going to be 0, 1, 2, 3, 4. Low is less than high, right? You keep on dividing the moment, even when you have 2 elements in the sub-array, correct? When you have, let's say, 7 and 8, your low is pointing here and high is pointing here, right? This is index number might be 0, this is index number 1. Still the condition of low less than high is there, and that is where when you have 2 numbers in your sub problem, you can still divide that sub problem further until you get a sub problem which has 1 number and another sub problem which is also has 1 number, right? Now the moment you have a sub problem which is only 1 element, your low and high are both going to be equal, right? Both are going to point to the same index, right? So that is why I've used this condition, unless and until the sub problems are at least, until you have at least 2 numbers in your sub problem, you can keep on dividing it. But the moment you have only 1 number in your sub problem, there is no need to divide, right? Because then that sub problem is already sorted. Right, so let's write this in code. So I've written a quick sort. Now this code will be available on the GitHub. I will link it down in the description. So I have written a quick sort function. So I have an array. I have a low and high, right? This is my low index and the high index, correct? When you're calling it for the first time, I'm calling it from my public static void main. What I'm going to do is I'm going to pass the name of the array. My low index is going to be the 0th index and the highest index is going to be the n minus 1, right? If the length of the array is given by a dot length, the highest index is a dot length minus 1, correct? Now going back to the function. So I'm going to do the if condition here. So if low is less than high, right? What I'm going to do, our first step in divide and conquer is to divide, is to partition, right? So here we're using the partition algorithm. So I've just written a partition function. We'll see the next how this partition algorithm works. But right now let's assume that this partition algorithm is going to give us the index. It is going to return us the index of the pivot element. If you remember, we just spoke about that partition algorithm will actually partition the array in such a way that the pivot element is present in its correct position. All the elements which are less than pivot are to the left. All the elements which are greater than pivot are to the right of it, right? So it is basically going to send you, the partition function is going to send you the index, this particular index, right? So the 0, 1, 2. It is going to send you index number 2 where that partition has placed the pivot element, right? So with that, you can now say that all the numbers between 0 to 1 belong to one part, one sub problem, and all the numbers going from 3 to might be 5 belonging to the second sub problem. That's what exactly I'm doing here. Once I know the partition index, I'm going to then call my quick sort on where low and partition index minus 1, quick sort which is partition index plus 1 and high. This is very similar. If you look at this is very similar to your merge sort code, right? So very similar to merge sort code. The only difference is in merge sort we used basically the middle, right? Middle equal to low plus high by 2. That formula we used. But here we are basically going to make use of partition algorithm. So this is the code which we'll write to for quick sort. Okay. Now let's try and dive into partition. Let's talk about how partition algorithm actually, partitions or divides your algorithm into, your entire array into 2 parts, right? It places the pivot in its correct position and divides it accordingly, right? So let's take an example to understand this. So the first example which we are going to take is, let's take we have 4, 1, 3, 9 and 7, right? We also taken this example before. Let's assume that this is our pivot element, right? So before we start this, let us talk about this pivot element, right? The only thing which I've told you so far is pivot is nothing but partition algorithm chooses the first element as your pivot element, right? Now, is it necessary that you should always choose first element as your pivot element? No, not at all. You have actually around 3 to 4 options of choosing your pivot element. The only thing is if you have chosen one option, it's better to stick to it, right? So for example, the first option of choosing your pivot is, which I have just now mentioned, is you can always choose the first element, right? Your first element of your sub array can always be your pivot element. The second option is you can always choose the last element as your pivot element. Third option is you can choose the middle element, or you can also call it as a median element as your pivot element, right? So between, suppose you have your sub problem, going from the range low to high, that is your indexes, then A of low, and suppose the name of the array is A, so A of low is always going to be your pivot. In the last element, it means A of high is going to be your pivot. If it's a middle element, you're trying to find out basically between low plus high by 2, take a middle element, and whatever index you get here, let's say mid. So A of mid is now your pivot element in the middle case. The last option is, which is called as using a random pivot element, meaning you use a randomized algorithm, right? So there are randomized algorithm which give you a guarantee that the probability of choosing any of the indexes which goes from index number 0, index number low to index number high is going to be equal. So every probability of choosing any of that indexes is equal. So you chose such random algorithm with which you place your, you just put into that algorithm, that in the random algorithm, that I want a random number between the index low and high, and it will give you a random number. You choose that index, okay, whatever element is present at that index, you choose that index as your pivot element, right? Like for example, if my low and high, okay, is going from index number might be 3 to index number 5. So how many indexes I have? Basically 3, 4 and 5, 3 indexes. You basically, if you are going to choose the last option of choosing pivot, you are going to use a random algorithm where the probability of choosing 3, 4 and 5 is equal. This is basically 1 by 3, right? Probability. So if the random algorithm gives you index number 4, okay, as the element or as the random index which it has chosen, that means that now you're going to choose A of 4 as your pivot element, right? Next time, suppose if the random algorithm gives you an index number 5, then you're going to choose A of 5 as your pivot element. That is what the meaning of random choosing a pivot element randomly, right? So there are 4 different options of choosing your pivot element, right? So now right now we're going to look at the code where we are choosing the pivot element always as the first element, okay? Stick to the at the end of the video. I will also give you a shortcut key. If suppose in the interviews, right, you've always been to write code by choosing the first element as your pivot element, right? But let's say the interviewer says no, you will have to use a method of, might be using the random method to choose the pivot element. How? There's only one change you need to do in the code, and your code, whichever code you have practiced for, the partition code which you have practiced for choosing the first element as pivot element will be used. You can convert all of these into the first one. So we just hang on to the end of the video and I'll give you that trick. Okay, so moving on. So right now we are choosing the method which is to find out the first, like our pivot is always going to be the first element of our subproblem, right? So here I have chosen what? 4 as my pivot, correct? So I'm just going to mention this is as my pivot element, correct? What should be the final output of our partition? 4 should be placed where actually its position is. Right now the 4's position is here, wherever 3 is. All the values which are less than pivot should be to the left of it. All the values greater than pivot should be to the right of 4. So what I'm going to do is I'm going to basically, the partition algorithm actually uses the concept of 2 pointers, right? So there's a way of solving problems which is called 2 pointers, in which you have 2 pointers here, as the name says. I have index 1, index I, which is basically this I, and the other one is J. Okay, what I'm going to do is I'm going to say, right, I'm going to check, is my 1, okay, less than or equal to pivot? Yes. And this is what I want, right? All the values which are to the left of pivot has to be what? Less than or equal to. So I'm going to basically make a check. Is A of I less than or equal to pivot? If this condition is true, I'm going to simply do I plus plus. So I'm going to say, because 1 is less than or equal to the pivot element 4, I'm going to increment I plus plus. Is 3 less than or equal to pivot? Yes. So I gets incremented, right? So now 9 is not basically less than or equal to pivot. So I'm going to stop my index I there. Let's start for index number J. What about this? Is 7 greater than pivot? So I'm basically going to check, is A of J greater than P? If A of J is greater than the pivot element, I have to do what? J minus minus. Why am I doing so? Because I do not have to do anything or rearrange this number 7, because my output of pivot, output of a partition algorithm should be like all the elements which are greater than the 4 number needs to be what? Appearing at the right hand side. Already the number 7, which is greater, it is actually greater than 4, and it is anyways towards the end of the array, right? So I do not have to rearrange those numbers. So that's why I'm not doing anything with them, and I'm simply decrementing my value of J. Now what am I getting? Is 9 greater than the pivot element 4? Yes. So I'm going to just move it one step closer to 4. Now, is 3 greater than the pivot element? No. So that's why I'm stopping my 3. Now, is 4 greater than the pivot element? Yes. So I'm going to just move it one step closer to 4. Now, is 3 greater than the pivot element? No. So that's why I'm stopping my 3. Now, is 4 greater than the pivot element? Yes. So I'm going to just move it one step closer to 4. j loop here. So right now my j is pointing at index at element 3, I is pointing at number 9, right? Let's try to see what exactly this has given us. Let's try to visualize, right? So let's say your j is basically your I. Let's talk about I first. Let's talk about this, right? Let's draw this. Here at index I, you have a number 9. Let me draw this. What that means is all the numbers which are to the left of 9, right? That means 4, 1, 3. All these values are basically less than or equal to the pivot element. Yes, only this number 9 is what? Greater than pivot. That is why we actually stopped our iteration of I, right? Similarly, where is j? J is here. Right now, j is here. Because let's say if I write the indexes here, index 0, 1, 2, 3 and 4. This is at index number. I has a value of 3. And right now j will have basically a value of 2. So that's why I've written it up to the left of I, right? So here I have j, the value is 3. Correct? All the values, okay, which are to the right of j, because if you remember we started our j right actually from the last index, right? All the values which are to the right of this index j are basically greater than the pivot value, right? Now let's try to combine these two observations. Look at this. All these values right now, see if I have to draw from here, right? These are all the values greater than pivot. Why can I say that? Because j is actually index number 2 and its index 2 is appearing before index I, which is nothing but value as 3, right? So all the values after index j, right, are the values greater than pivot, correct? All the values which are to the right or to the left of my j index are what? Less than or equal to pivot, correct? Only thing which is not confirming is this numbers, right? 9 and 3, right? What we just now said is all the values, okay, which are in this part, which are where, which are basically to, all the index, all the elements which are present at index greater than j, which means all the values like 9 and 7, these values are greater than 4, correct? And that's what you want. Okay, now tell me, should I do anything with the value which is present at index I? No, it is already in its correct position, right? Because if you look at this is what we have, right? 9 and 7 anyways are greater than pivot, and that's what we want in the final output also. So I need not do anything here, right? This has already been sorted. I mean sorted as in I have what I want, right? What about this part? What about this part? Or let's take it here, right? From here. If you look at this, in this first thing, right, with this index I, okay, that first index I, wherever it has stopped, it has told us that all the values which are appearing before this index I are supposed to be less than or equal to pivot, correct? Here also you have number 3, which is less than or equal to pivot. It's going to satisfy this. Okay, now what I need to do is, my job is, now I also have kind of divided my array into 2 parts. All these values are what? Greater than the pivot. All the values are less than the pivot, right? Now what I need to do is, the only job which is remaining for me is to place this pivot in its correct position. Tell me, what is the correct position of 4? The correct position of 4 is, if I swap this position with the element which is present at index number j, will I get 4 in its correct position? Absolutely. So what I'm going to do is, I'm going to swap. I'm going to write here, I'm going to swap, okay, a of low, that is basically my pivot element, along with a of j. If I swap these two, I'm going to get array like this. 4 is, let me write it here so that becomes very easy to see. Here what I'm going to get is 4 will be placed here and 3 will be placed here. By doing so, what I have achieved is, all the values which are less than or equal to the pivot element 4 are to one side. All the values which are greater than pivot are on the other side, and the pivot element is in its correct position. Because if I had to sort these numbers, my numbers would look like 1, 3, 4, 7 and 9. 4 is, the pivot element is exactly in the position where it should be if I had to sort these numbers, right? I hope this is making sense to all, right? So this is basically one part of partition algorithm. So this is the first case, right? So let me now summarize what I have seen so far. What I have done, whenever my value of I, right? And value of j. What can I say? I value was greater than j. If you can see, index I is nothing but stopped at what? Number 3. Now what is the index j? It is number 2. So what is true about this? I value is greater than j. When I value is greater than j, I have to simply swap the partition element, the pivot element, which is basically placed at A of low. So I simply have to swap the pivot element with A of j. Yes, if I do so, my job is done. And can I just stop my partition? Yes, your job is done because your partition algorithm has done the job of dividing the array into two parts, and your pivot element is placed in its correct position. Correct? And I can simply move on, right? This is one case, right? Now, let's talk about another case. For another case, let's take the second example. Suppose if I had 11, right? You have 12, 10, 13 and 14. Now, as we had discussed, we are going to take this as a pivot element. So let me write here pivot. I'm going to have I and j here. What did we say? All the values needs to be less than or equal to the value of a of I. So can I say something like this here also? If my a of I, if this value is less than or equal to my pivot value, I'm going to simply increment my I plus plus, right? Tell me, is 12 less than or equal to pivot? No. So I'm not going to increment and my I stops here, right? Similar thing I have to do also for what? For the index number j. What this has to be? My a of j, right? A of j needs to be greater than pivot. As long as this condition is satisfied, I can decrement j minus minus, right? Think about this, 14 and 11. 14 is greater than 11, j minus minus, right? Because anyways, after the output of the partition should be all the elements which are greater than pivot should be to the end of the array. So anyways, we have nothing to do with 14 and it is in its correct half of the array, right? Similar, 13 and 11, 13 is greater than the pivot value 11, so j minus minus. What about 10? 10 is not greater than 11, right? So that is why I'm going to stop my condition here. So here what case is getting? Here I have a case where index I is less than j, which is different from my earlier case. Here what I had exactly opposite. Index I was greater than index j, and that's why I swapped pivot with a of j. Here what I have is index I is less than j. We need to find out what we need to do in this scenario, right? Because there are only two scenarios, right? If you have two pointers, I and j, and you're basically moving those pointers, right? You are incrementing one, right? Basically, this I is moving in this direction and j is moving in this direction, right? They're basically moving towards each other. There are only two possibilities which are possible. One possibility is either I is less than j, and the other possibility that I is greater than j, right? We have just seen for what we should do if I is greater than j. We said that we will swap the pivot with a of j and our partition is over. Let's talk about when you have the scenario where I is less than j. In this scenario, tell me, let's try to even visualize what has just happened. You are stopped at an index I. All the elements which are to the left of it are less than or equal to pivot, right? That's how we have actually even ran our loop. What about j? All the elements to the right of it are greater than pivot, right? Only thing is this is not complying, right? Whatever element was present at index number I, we stopped there because this element was greater than pivot. And here the element was less than or equal to pivot. Now tell me, this was only the odd man out. If we have to stabilize this, what we need to do? Can we simply swap this? If I swap this, what is going to happen is there was a number at jth index which was less than or equal to pivot. I'm going to move this element where at index I, and whatever element which was at index I which was greater than pivot, I'm moving it where? Here. Let's take an example. Suppose if I had here, might be here what we had 10 and 11, right? I think so. Here we had the number is 12 and here the number is 10. Our pivot value is what? 11. So basically all the values to the left of 12 are less than or equal to the pivot value, right? Only this number is greater. If I swap this, what I'm going to get is I'm going to get a 10 here and I'm going to get a 12 here. Does it now satisfy the conditions which we want? Yes. Now I can say all the values which are less than or equal to the pivot are to what? Are to there's one part to it. All the values are greater than a pivot are starting from index number j, right? So now your array is going to look something like this. Let us just change this. So we are going to have here now, here I'm going to have 10, here I'm going to have 12. So now we have an array where this part has elements greater than the pivot, this part has elements less than the pivot. So we have just performed one step. Tell me, is your array right now, the array which you have forgot, right? We just did this step. Is it completely, like, is the entire job of partition over? Not really, right? Yes, this part, yes, I have all the elements which are basically what? Greater than, pivot. All the elements here are, less than or equal to pivot. But there is one problem. The pivot element is not placed in its correct position. That is also one of the outcome of partition algorithm. That means when you have this condition when I is less than j, all you need to do is, you need to do two things. The first thing you need to do is swap a of I and a of j. After you do that, you need to continue the partition process because we have still not placed the pivot element in its correct position, right? So these are the two cases which are possible when it comes to partition algorithm. So partition algorithm in itself is based on the concept of two pointers, right? So we have two pointers and we work, basically we try to, look, when we are trying to draw logic for the partition algorithm, just remember what should be the end output of the partition algorithm. You want to divide your array in such a way all the values which are less than the pivot should be on the left hand side, all values which are greater than the pivot should be to the right hand side. So you just use those two loops. You are always going to end up into either one of the condition. Either I is going to be greater than j. If that is your case, you swap pivot with a of j. If I is less than j, then you swap a of I and a of j and you continue your partition process because the pivot is still not placed in its correct position, right? Let's try to look at the code for this. So the code is very simple, and when you look at the code, or might be from the algorithm also, it would have been clear that the partition algorithm actually takes O of n time because there's only one loop, okay? You're going to visit every element only once. So that's why it's going to take linear time complexity, right? So here, as I told you that the pivot is here, I'm going to show you the code, which basically takes always the first element as your pivot. So int pivot is equal to A of low. I have I index basically low, j index equal to high. Now while I is less than j, right? While I is less than j, right? Why are we doing until I is less than j? Because the moment I is greater than j, which we saw here, right? When I was greater than j, your partition has to stop. Why? Because you have also partitioned it plus you have put the pivot element in its correct position, right? So that is why I'm going to have this condition for stopping my partitioning process, right? While I is less than a dot length and a of I is less than or equal to pivot, I'm going to do I plus plus. Similarly, I'm going to do for the j. Until a of j is greater than the pivot, I'm going to do j minus minus. I hope this conditions you understand. This is basically to make sure that you do not have array index out of bounds, right? You do not go beyond a certain index and you do not go like -1 index, right? Because -1 does not make sense as index, right? Then if I is less than j, which we saw, then what we have to do, we simply have to rearrange or swap a of I with a of j. I've written a special function basically for it, which will do the job of swapping two numbers. I pass in the array, the indexes which I want to swap, and it is going to do the job of swapping for me, right? That's all. You can also write it here. It's just to write a clean code. That's it. So if I is less than j, I'm going to swap. But do I stop my partitioning? No. You do not stop your partitioning as long as your I is less than j. Okay, the moment your I becomes greater than j, then what you do, you come out of this while loop, you swap now a of low with a of j because you're basically placing the pivot element which is at a of low in its correct position, right? And what we saw when we did this, when we saw the code of quicksort, we want to basically have the index at which the pivot element was placed, because that is going to now help us to divide your array into two parts. So you're going to return what? Index j. Why? Because at index j only your pivot element was placed. So this is the entire code for partition. So I have seen a lot of students actually getting confused in partition algorithm. Just remember the things which I told you, right? When you're studying partition algorithm, try to remember in this sense that what is the end goal of partition. There are two things. One is you have to rearrange the array into two parts, and second is placing the partition in the correct position. You use two pointer approach. So you have I and j pointers. Both of them are going to, traverse towards each other. Because they're traversing towards each other, there's only one of the possible situation. Either I is less than j, या फिर I is greater than J. In both the cases I showed you. The first example one talks when you have I greater than J, what you should be doing, and when I is less than J, what you should be doing. Remember these two examples and you should be good to go. So time complexity for this partition algorithm is O of n. Okay, now we had spoken about different ways of choosing your partition algorithm, right? And I told you do not really need to go ahead and remember 4 different versions of partitioning. No, there's a small trick which I'll be telling you right now. See, there were 2, 3, 4 ways, right? And you know the code of when your first element is your pivot element, correct? Now all you need to do is, okay, suppose if you had to choose your last element as your pivot element, why can't you swap simply the value of your last element with A of low? Once you do that, right, now whatever, see, it's not about the index which you're choosing, it's basically about the element, right? You're basically now saying that the last, whatever element is at the last, I'm going to always choose it at pivot, right? So why not I take that and put it in the first position? Once I do that, I've actually chosen the last element as my pivot. I just change its position, and now can't I use the version of partitioning which I know, which is partitioning when the first element is chosen as partition. Simple. Similarly, if you had to, suppose if you wanted to write a partition algorithm where you're choosing the middle element as always your partition element. So find the middle element, then swap A of mid with what? A of low. And now you can use the first version of your partitioning. Similarly, if you had to find out if you had to use random method of finding your pivot element, find that random method. Let me call it that index as random. Now I'm going to basically swap A of random with A of low. And now I'm going to use what? The first method of partitioning. That means in the code, where should I make the change? Simple. Where you're choosing this pivot, right? Before this, whatever line you have, suppose you had to do A of low, right? So what you have to do, your A of might be high is always going to be your what? The pivot element, right? So simple, do a swap. Swap of what? Swap your A, swap A of low and high. Swap this two indices, and then what you can do is simply continue this. This is where I am choosing what? My partition element as always the last element. Instead of this, if you had to choose random, you write the code of random. If you had to do choosing middle element, find the middle element or the middle index and then swap your low with the middle index, right? That's only those two lines you will have to write. Entire code remains as it is, right? So I hope you've understood this partition, right? We have seen this quick sort, right? Now if you just run this code, this is going to basically sort your values in ascending order 1, 3, 4, 7 and 9, right? So I'd given the input here 4, 1, 3, 9, 7 and this is your. Let's talk about the time complexity of quicksort algorithm, right? Now for time complexity analysis, let's say that T of n, right, is the time required or the time complexity for sorting an array which has n numbers, right? Total number of n. So what, because we are using divide and conquer for quicksort, what is it going to do? It's going to divide this n into 2 parts, right? And keep on dividing it. Now, depending upon the partition algorithm which we are using and the number of ways, the ways in which the way in which these numbers are arranged, right? It is possible that you can have, okay? It is possible that you can have the partition element placed in such a way that the n, okay, this number gets divided into something like this. Your partition element or your pivot element is here, right? And remaining n minus 1 elements, right, are present to the right of it, right? Or else it can be all the n minus 1 elements are present to the left and the pivot element is present at the end, right? That means this is possible if this case is possible if your pivot element, the pivot element which you chose is basically the smallest element in the array. In that case, your array is going to get divided into something like this, right? Suppose if your array was already sorted, right? And let's say you're choosing the first element as the pivot element. What the partition is going to do? Partition is not going to do anything. It's going to say that, okay, 1 is already present in its correct position and remaining part is this. How many elements are present now in this subproblem? N minus 1, right? So now from T of n is now divided into, you have one subproblem which has size of 1 and another subproblem which has size of n minus 1. And to do this subproblem, okay, to get this subproblems, how much time did we take? We basically use the partition algorithm, and that has taken how much of time? O of n, right? Partition algorithm is a linear time complexity, so O of n. So this is how your recurrence relation would look like. Suppose if you had it like this, I can also do the other way around. Suppose if I had something like 4, 3, 2, 1, right? And let's say I want to basically sort this in ascending order, this array. I'm choosing this as my pivot element. This 4 is going to get placed in its correct position. All the numbers, remaining numbers, are going to be to the left of it. Again, the array is divided into two subproblems. One is size of n minus 1 and another one is the size of 1. So again, I'm going to end up with this equation. T of n is equal to T of 1 plus T of n minus 1 plus O of 1. O of n, right? Now, can I just ignore T of 1? Yes, because T of 1 basically says that it is the time complexity required to sort an algorithm when the number of elements present in that array is 1. We know that if the number of elements present in an array is 1, that array is already sorted. There is no requirement of any processing, right? So it's basically constant time. So can I say T of n is equal to T of n minus 1 plus O of n required for partitioning. This is basically going to be the worst case scenario for the quicksort algorithm, right? Yes. If you solve this recurrence relation using Master's theorem, this is going to give you O of n squared. So quicksort algorithm in the worst case is going to give you what? O of n squared time complexity, right? What about the best case scenario? Now, as you must have guessed, best case is possible if somehow the algorithm is going to divide the array into two parts. It need not be exactly n by 2, right? But we can have, might be here 3 elements, here 2 elements. This is still fine, right? Something not like n minus 1 on one side. That is something will give you worst case, right? So if we could divide an algorithm something like this, okay, if I can say n by some k plus 2 of T of might be, let's take some another value k dash, okay, k dash, or let me write it like this, n divided by k dash plus O of n, right? Now, actually, in the analysis, they have found out that if I could divide my array something like T of n by 9 plus T of 9n by 10 plus O of n, this is going to actually give me basically O of n log n. That means if I solve this, okay, T of n by 9 plus T of 9n by 10 plus O of n, if I was able to divide my subproblem in such a way that one part has 1 by n elements, another part has 9 by 10 elements, I can still end up with O of n log n time complexity, right? This is basically, actually, this is actually the average case of quicksort. Now, what about the best case? Best case would be if I could exactly divide into two parts. I can say T of n is equal to T of n by 2 plus T of n by 2 plus O of n. This is actually gives me again O of n log n, which is your best case. That means the best case and average case of your quicksort algorithm is O of n log n, but you can run into a worst case if the partition algorithm is going to partition your array in such a case that n minus 1 subproblem is of size n minus 1. In that case, you're going to run into a time complexity of O of n squared. So this is about time complexity analysis of quicksort. What about space complexity? Do we require any extra space other than the space required to, store the input? No, not surely. So this is basically you do not require any additional space. So the auxiliary space complexity or the space complexity in terms of processing the quicksort is basically O of 1. It's basically your constant, your sorting algorithm, right? Hope this helps.